In this video, our goal is to be able to write an electron configuration for any atom of an element. So in order to be able to do that, we need to have some understanding of the structure of the quantum mechanical model of the atom. So we have a few different levels of organization in the atom. The kind of smallest unit is known as an orbital. So an orbital is just a region of space around the nucleus where an electron is able to exist at a particular energy. Orbitals are grouped into subshells of similar energy and shape. So there are four fundamental shapes of orbitals. They're known as the S, the P, the D, and the F. S orbitals are essentially a sphere, so I have kind of little sketches of them over here. And there is one S orbital in an S subshell. The P is often described as a dumbbell shape. It's sort of this elongated two bubbles connected in the middle. And there are three P orbitals in a P subshell. Next, we have the D, which is usually described as a four-leaf clover. They actually come in a couple different shapes, but 4 out of 5 of them are shaped like a four-leaf clover, so that's a fine image to have. So they look something like this, keeping in mind that these are in 3 dimensions. So each of these little leaves on our clover is actually a balloon type shape, not a flat leaf. And there are 5 d orbitals in a d subshell. And then last but not least, we have the F orbital, whose shape is best described as complicated. Many of them are kind of like 2 d orbitals sort of back to back, essentially the 8 balloons pointing towards the corners of a cube. But there are a few other shapes as well. Essentially, don't worry about it. Complicated is good enough to know. But you should know that there are 7 F orbitals in an F subshell, and that the order I have listed these in within the same shell, which is our next level of organization, the S to P to D to F is listed as the lowest energy to the highest energy within the same energy level. So orbitals are grouped into subshells. Subshells are grouped into shells, which are also frequently referred to as energy levels or sometimes N levels. And these are just a group of subshells where the electrons are all a similar distance from the nucleus is really what's similar here. So we group orbitals into subshell by shape and energy. We group subshells into shells according to distance from the nucleus, where our electrons are being held. Different shells contain different subshells. They don't all have them all. Essentially, we start with the lowest energy and we kind of add them on as we increase our energy levels. So the first shell, often known as the N equals 1, is the closest shell to the nucleus, and it is the lowest energy, and it only contains a 1s subshell. That is all. So it only contains an S subshell, which we call the 1s. So we label the subshells with the shape of the orbitals and the shell that they are in. So the S subshell in the first shell is referred to as the 1s subshell. The next shell up, the N equals 2, would be a little bit farther away from the nucleus, contains S and P subshells, and that's it. So we've added 1 on to our list of subshells. Because they're in the second energy level, we refer to those as the 2s and the 2p. The third shell is known as the N equals 3, would be even farther away from the nucleus than the N equals 2. We're adding a third subshell into the mix here, S, P, and D, which were known as the 3s, the 3p, and the 3d. And then the N equals 4, we get to all 4 of our shapes finally, the S, P, D, and F, which would be known as the 4s, 4p, 4d, and 4f. After that, for our purposes, we still just have those 4 subshell types. Technically, there are others. After F, we just go in alphabetical order, but there are currently no elements that use any other type of subshell in their ground state, so we don't usually think about that. But technically, the N equals 5 would also contain a G subshell, but we don't ever use it, so we're not going to talk about it or think about it. So as for the purposes of this course, Everything n equals 4 and beyond is effectively the same in terms of its contents. It's just farther and farther away from the nucleus, the higher your shell number gets. So electrons like to spend most of their time in the lowest energy orbital available to them. So our goal for this video is really to be able to write an electron configuration, which is describing what orbitals each electron is in your atom. And so we typically express that as what we call the ground state electron configuration, meaning the lowest energy configuration possible. Higher energy states, known as excited states, can be entered when an electron absorbs a photon, but the electron doesn't usually stay there. It absorbs some energy, goes to a higher energy orbital for a little bit, and then usually spits that energy right back out and goes back to the ground state or some lower energy state. So when we're figuring out our ground state arrangement for electrons, there are 3 rules that we need to follow. First and foremost is the Pauli exclusion principle, which tells us every orbital can hold a maximum of 2 electrons, no more, and electrons in the same orbital must have opposite spin. So electrons have a property known as spin, which is really related to magnetism. They're not like little tops, but we call them spin up and spin down. So electrons are typically represented in diagrams as little arrows, and you'll often see them pointing up and down, which is representing the spin of those particles. So if they're in the same orbital, they have to be going in opposite directions. You cannot have 2 electrons in the same orbital with the same spin. That is a violation of the laws of quantum mechanics. The second rule is known as the Aufbau principle, which tells us that electrons will occupy the lowest energy orbitals first. So we're going to talk a little bit more about the overall energy order of things in a sec, but you always start at the bottom energy-wise and build up from there. And the third and final rule is known as Hund's rule. That tells us when orbitals are degenerate, which means that they have the same energy, which is true for orbitals in the same subshell. You want to put one electron in each of your orbitals before you go back and start pairing them up. This is sometimes referred to as the bus seat rule, that when you're getting on the school bus, everybody wants to have their own seat until all the seats have one person in them, and then people start sitting together. And also Hund's rule says that all of our unpaired electrons must have the same spin. That one's not as big a deal, but it comes up every now and then. So these 3 rules must be followed for the ground state. For higher energy states, for excited states, we can break some of these rules, not all of them. So excited states are allowed to violate the Aufbau principle and Hund's rule. Those 2 rules, numbers 2 and 3 that we just talked about, describe how electrons get to the lowest energy state, but they're not fundamental laws of quantum mechanics that must also always be followed. However, the Pauli exclusion principle is a fundamental law of of quantum mechanics, and that one cannot be broken. So excited states cannot violate the Pauli exclusion principle, but they may violate Aufbau, Hund's, or both. Any violations of the Pauli exclusion principle are impossible. They're not excited states, they're impossible. Excited states can happen and do happen. Violating the Pauli exclusion principle does not. So this brings us to kind of our goal here, which is writing electron configurations. So the electron configuration for an element just describes the location of all of the electrons in an atom. It tells you which subshells actually have electrons in them and how many electrons are in each in order of increasing energy. So for instance, when we're following all the rules, Aufbau, Hund, and Pauli, for hydrogen, we're going to put its 1 electron in the lowest energy orbital available, which is the 1s. So our 1s subshell will contain 1 electron. So we write the shell number is 1, the subshell shape is s, and the number of electrons here is 1, is written as a superscript typically. Going on to helium, we have 2 electrons that we need to put in the lowest energy orbital, which is the 1s. So this would be written as 1s2. They're in the same subshell, but we now have 2 electrons in there instead of 1. Moving on to lithium, we have 3 total electrons that we need to place. The first 2 can go in the 1s orbital, but then after that, the 1s is full. The Pauli exclusion principle tells us that an orbital can hold a maximum of 2 electrons. So after that, we need to move on to our next subshell, which is the 2s. So our electron configuration would be 1s2, telling us that there are 2 electrons in the 1s subshell, 2s1, telling us that there's 1 electron in the 2s subshell. So this is our complete electron configuration for lithium. Now we can figure out the order of the subshells directly from the periodic table. So our periodic table's shape really comes from the quantum mechanical structure of the atom, that these first 2 columns on the left are where an s orbital is filling up, where your last electron was added to an s subshell. So we call this the s block. The p block is these 6 columns on the right here. Anytime you're moving through the p block, adding electrons, you're putting them in a p subshell. The d's are in the transition metals. So as we move through the transition metals, we're putting electrons into d subshells. So we call this the d block. And then the lanthanides and actinides down here, the island of misfit elements, is known as the F block, because as you're moving across that block of the periodic table, you're adding electrons into an F subshell. So we can write an electron configuration by identifying where are we on the periodic table and just filling everything up until there. So let's look at arsenic as an example. So it is in the P block in the n equals 4 row. So arsenic is right about here on the periodic table. So that means everything up until arsenic is going to be filled. That our S block here, the first shell that contains an S subshell is the n equals 1. So we start in this block at the 1s, and then as we move down, we're moving up in shells to the 2s and the 3s and so forth. Our P block starts at 2 because the first shell that contains a p orbital or p subshell is the n equals 2. There is no p subshell in the n equals 1. So the very first row of this block is actually number 2, and then we continue 3, 4, 5 onwards from there. In the D block, the first shell where we find a D subshell is the n equals 3. There's no such thing as a 1D, there's no such thing as a 2D. 3 is the lowest that we've got. So the first row of this block is 3D, and then we go 4, 5, 6 as we move down. And the first shell that contains an F subshell is the n equals 4. So this starts at 4 and then goes on to 5. So if we want to write our electron configuration for arsenic, we just need to work our way through the periodic table, and everything up until the 4p is going to be completely filled. So our 1s can hold a maximum of 2 electrons, or 2s. So when we fill up the 1s, the next place we go is to the 2s. Then we're over here in the 2p, which can hold 6. Then we get to the 3s, which can hold 2. Then we get to the 3p, which can hold 6. Then to the 4s, which can hold 2. The 3d, which can hold 10. And then the 4p, we just need to count how many spaces over we are. We've got 1, 2, 3, 4. So since arsenic is the 4th spot in the 4p row, that means the 4p subshell is going to contain 4 electrons. So we can use the periodic table in this way to write electron configurations pretty simply, as long as we remember which portions represent which subshells. So we can also abbreviate our electron configuration by referencing the previous noble gas. So essentially you're just going backwards in the periodic table until you find a gas, or a noble gas, sorry, until you get to that last column on the right, and replacing that noble gas's electron configuration with just the symbol for the noble gas in brackets. So in the case of arsenic, which we just wrote, also I just made a mistake, sorry. Arsenic is 3rd, not 4th, my bad. So this would be 4p3, apologies for that. So when we go backwards from arsenic, we get argon is the previous noble gas. The configuration for argon is 1s2, 2s2, 2p6, 3s2, 3p6, which corresponds to this whole chunk. In the configuration of arsenic, those two things are the same. So all we're doing is replacing that with the symbol for arsenic in brackets, and then listing everything that comes after, saying that arsenic is like argon plus this extra stuff.